Ionization energy we talked about a little bit. This is the energy that's required to make an ion with a positive charge. So really, I don't like this term because I could add an electron to an atom and make it a negative charge. It's still an ion. An ion has a charge. It doesn't say whether it has a positive or negative. So ionization energy really should be called cat ionization energy. A cation is one with a positive charge. So really what we're talking about here is, how do I make this atom into one that has a positive charge? The only way to do that is by knocking an electron out. Right? So if we want to knock an electron out, that requires energy. It's a positive quantity of energy because it's energy that must be absorbed by the atom. This is the same type of thing we saw in the last chapter in the photoelectric effect. Right? We had the photoelectric effect. We had a piece of metal. We hit it with light. The light energy is converted into potential energy as an electron in the metal lost its attraction and moved to a higher energy level. If the light energy was above the threshold necessary, then it had a large quantity of energy, it would take one of the electrons in the metal and knock it out completely from the atom. That's ionization energy. The electron in the metal has some attraction. Even if there's a lot of shielding, it still experiences some effective nuclear charge. It still has some attraction. If you want to overcome even a small amount of attraction, you need some energy to break that attraction. So the potential energy of the electron increases. The ionization energy is the amount it increases by. More ionization energy, meaning I need more energy to break that attraction. The attraction is stronger. So that's what ionization energy is. And we're making a cation here, not an anion. So here are some ionization energies. We can see a trend here. Generally the trend is, as we go up, the ionization energy increases. As we go to the right, the ionization energy increases. If I ask you to rank ionization energies, it's not adequate to say this element is farther, closer to the top than the right, so it has a higher ionization energy. It's not a reason. The reason that the elements at the top have higher ionization energies is because they have less shielding. With less shielding, the electrons are held more tightly. So it takes more energy to overcome their attraction and knock them out. The reason that as I go to the right, ionization energy increases is because I add more protons. With more positive charge in the nucleus, I have a greater attraction. Even though there's similar amounts of shielding for elements in the same row, adding more protons pulls them closer, and I need more energy to overcome that attraction. So there are some other factors that explain some of these trends. So we're going to look at one other factor, and that is whether or not you have an exactly full or exactly half-filled subshell. And that explains some of these areas here. So just to point out, first of all, on this graph, this going from lithium to neon is an increase, right? Because lithium to neon are all in the same row. So as I go from left to right in that row, from lithium to the other elements in that row up to neon, generally I'm increasing because I'm adding more protons. So this is going up on the graph because I'm increasing the number of protons in the nucleus. That means it takes more energy to overcome that attraction, higher ionization energy. This trend from helium to neon to argon and down, that's the trend as we go down the periodic table. So as we go down the periodic table, I have an increase in shielding. When I have an increase in shielding, I have less attraction for the electrons, so it doesn't take as much energy to knock them out, lower ionization energy. So that explains the general trend, but it doesn't explain why this goes up and then comes back down and then up and back down. Why isn't it just straight up? Okay, so to explain that, we have to talk about how the ionization energy is affected by having exactly full or exactly half-full subshell. So in this particular case, we're looking at these two elements right here. Oops. Right here. Lithium. The next element over is beryllium. This is beryllium's ionization energy. it's slightly higher than the next element, which is boron. Generally, the trend would suggest that as I go from beryllium to boron, the shielding is similar, and so if I add another proton, it should have a higher ionization energy because it's going to take more energy to overcome that attraction. But the actual subshell that the electron in makes a difference. So since boron's outer electron is here in this subshell, and this outer subshell is neither exactly half full or neither completely full, this electron is not going to be very stable. So the energy required to knock that electron out is a little bit less than the energy required to knock this electron out from an exactly full subshell. So it takes a little bit more energy to knock that out. That's why the energy required to knock an electron out of beryllium is a little bit higher than the energy required to knock an electron out of boron. So you should be able to make that explanation as well. And then the next one is here. The difference between nitrogen and oxygen. Right, so nitrogen has this orbital diagram. Its ionization energy is here. Oxygen is slightly lower. Normally we would predict as we go to the right the ionization energy should increase because we have more protons. But another factor that we need to consider is where are the electrons, how are they arranged? Because nitrogen has an exactly half-filled subshell, it takes a little bit more energy than normal to break that arrangement up and knock an electron out. So it has a slightly higher ionization energy. Because oxygen does not have an exactly half-filled subshell and can make an exactly half-filled subshell by knocking that one electron out, it is a slightly easier to knock that electron out. It takes a little bit less energy than normal to knock that electron out, so it has slightly lower ionization energy. Right? So you should be able to explain those trends that occur within a row, given your ability to draw orbital diagrams and recognize when an electron has an exactly half-fill or exactly full subshell. You can knock more than one electron out of an atom. Just finish this off real quick. We'll take another quick break. The first electron is always easiest to knock out. Once I knock an electron out of sodium, and now it has a net positive, that electron I knocked out is no longer doing any shielding because it's not in the atom. The remaining electrons have less shielding, and so they all get pulled closer to the nucleus. So what students will incorrectly explain this sometimes. An incorrect explanation is to say, once I knock an electron out, I have more positive charge. That's not true. You still have the same amount of protons in the nucleus. You could say you have a greater effective charge because now you've lost this electron, you have less shielding. So the remaining electrons are able to feel the amount of charge that was there more effectively and move closer to it. So this will make the atom smaller, and since the remaining electrons have a greater attraction now because there's less shielding between them, it will make the next ionization energy much higher. So the second ionization energy, the energy required to knock a second electron out from sodium and give it a +2 charge, is much higher than the first one. So here we can see a variety of ionization energies for the first few elements on the periodic table. These are the energies required to knock all the atoms out. You can knock all the electrons. You can knock all the electrons out of an atom if you have enough energy. So if we look at maybe fluorine, to knock the first electron out of fluorine, it's a pretty high amount of energy. Why does it take more energy to knock an electron out of fluorine than oxygen? It's smaller because it has more protons in its nucleus. More protons, greater attraction, takes more energy to knock the electron away from it. So once I knock one electron out, I'm going to have F+. Then if I want to knock the second electron out, it's going to take even more energy. That'll make F+2. Then I want to knock another one out. The energy starts to grow more and more. It's harder to keep knocking electrons out when the remaining electrons have less shielding and they get closer and closer and closer to the nucleus. For each one of these elements, though, there's at least one spot where there's a giant jump in the amount of energy. That's what this blue highlight shows, where the jump is, this giant amount of energy. What does that represent? For any one of these elements, at some point there's a big jump in energy from one ionization energy to the next. Why is that? What? Yeah, now we're talking about a different energy level. Right? So, for example, looking at carbon. I want to knock, for carbon I can knock 1, 2, 3, 4 electrons out. Each one of those requires a lot of energy. But then when I try to knock the 5th electron out, it takes a huge amount of energy. And that's because that 5th electron comes from a new energy level. Right? So if I look at carbon, if I knock 1 out, it'll have the same as boron. If I knock 2 out, it'll have the same as beryllium. If I knock 3 out, it'll have the same as lithium. If I knock the 4th electron out, which is requiring this amount of energy, then it will have the same number of electrons as a noble gas. So when it has the exact same number of electrons as a noble gas, then it takes a lot of energy to knock another one out, because that's a stable arrangement. And so far for carbon, I've only been knocking electrons out of the 2nd energy level. Now that that energy level is gone, the remaining electrons are in the 1st energy level. There's no shielding for those. They're right next to the nucleus. That's why it takes a huge amount of energy to continue to try to knock electrons out of the atom. Right? So this table demonstrates that, for carbon, these numbers are not that big. So when I have an element, even like for fluorine, fluorine, to knock an electron out of fluorine doesn't take that much energy. But to knock an electron out of a noble gas, it takes a lot more energy. So if I have like sulfur, I'm trying to determine how much energy it's going to take to knock an electron out. Sulfur is not a noble gas. And by knocking an electron out, I will not make the same number of electrons as a noble gas. So I can't use the noble gas configuration as an argument there. But if the element already has a noble gas configuration, because I've already knocked so many electrons out that the remaining electrons are the same as one of the noble gases, then I can say the ionization energy will be very, very high. Because once it has the noble gas configuration, that exact configuration imparts a lot of stability on the atom. So let's just do this quick example. Which will have a greater first ionization energy, sodium or magnesium? Yeah, magnesium. Right. So for magnesium, I'm thinking about for its ionization energy. I want to knock one of its electrons out. That electron's in the 3rd energy level. It's shielded by the first 2 energy levels, so there's a fair amount of shielding there. For sodium, I want to knock 1 electron out. Its electron is also in the 3rd energy level, shielded by the first 2 energy levels. So there's not a big difference in shielding. So I got to go to another factor. Magnesium has 12 protons, sodium has 11. So to knock an electron out of magnesium is going to be a little bit more difficult. There's an extra proton attracting it in. So that would suggest it should have a higher ionization energy. When the noble gas configuration is in play, that should be my major factor, though. Right, so if I were comparing aluminum and silicon, neither of those can make the same number of electrons as a noble gas by losing 1 electron. So that argument's not in play. But for these two, it is. Because for sodium, losing 1 electron, we talk about the first ionization energy, gives it the same number as a noble gas. That's not true for magnesium. For magnesium, losing 1 electron doesn't give it the same number as a noble gas. So that argument allows me to recognize that sodium's ionization energy will be way lower than magnesium's first ionization energy. What about the second ionization energy? Which of those two will have a higher second ionization energy? And then the answer will be sodium, right? Because the second ionization energy is energy it takes to knock a second electron out. So then I've got to compare the Na, which already had 1 knocked out of it, which will have 10 electrons, versus the magnesium already having 1 knocked out of it, which would be 11. So then I'm asking, is it easier to knock an electron out of an atom that has 10 electrons, or easier to knock an electron out of an atom that has 11? Well, it's way easier to knock one out of the atom that has 11 because that will give it the same number as the noble gas. So in that case, the magnesium will have a much lower second ionization energy than the sodium. And we can see on the chart where that's true. Actually, that we can't because it doesn't include the third energy level. So, but we could make the same comparison for lithium and beryllium. The second ionization energy for lithium is very high. The second ionization energy for beryllium is much lower. Right? Because once I get that noble gas configuration, it takes a lot of energy to break it up. And if I'm one away from that noble gas configuration, it will take a little amount of energy relative to knock that out and make the noble gas configuration. That's much easier to do.